All right, welcome to our fourth part and kind of final part, finally, of the Chapter 9 discussion for our recorded lectures. Today we're going to be talking about something that's a little bit different and not quite as directly connected to a lot of the things that we've been talking about, but something that is often looked at kind of in conjunction with those things and trying to really figure out as much information about a compound as you can. And that's going to be molecular orbital theory. So kind of bear with me as I'm talking about some of the different points. The start of this will be a little bit theory heavy and kind of the background of where it comes from. But hopefully by the end, when we actually talk about what are kind of the applications, what things do we want to take away, it won't seem so bad in terms of what we really want to focus on. So what exactly is molecular orbital theory? Well, it is a totally separate model from valence bond theory. Like the two do not really kind of coexist at the same time. Like you usually talk about one or the other when you're talking about a molecule in terms of like the type of information you're trying to find, because they do kind of serve different purposes. And that doesn't mean that one is wrong and one is right. They are just different, and they both have strengths and sometimes weaknesses then as well. And so we'll talk a little bit about kind of each of those. But it does focus mostly on covalent bonding. So MO theory is typically going to be used to talk about and describe different types of covalent bonding. And the big difference is that previously in our valence bond theory, we talked about all of the orbitals that are on just like individual atoms, right? And how like orbitals on the neighboring atoms can each basically overlap, and you get orbital overlap between the atoms that creates your bonds. Molecular orbital theory works a little bit differently. Molecular orbital theory actually kind of goes back to the start of what we talked about with quantum mechanics. And instead of talking about our electrons belonging to one atom and having orbitals on a single atom, molecular orbital theory takes a slightly different perspective and really just looks at things as, what are the orbitals on the whole molecule? So if you imagine almost solving like the Schrodinger equations for molecules instead of atoms, which can get much more complicated. And so actually getting the molecular orbital diagrams can be that we'll talk about later can be a pretty involved process for a lot of larger molecules. So for our sake, we're only going to talk about diatomic molecules, things with just two atoms, to keep things relatively simple. At least just give us kind of a couple pieces of information so that when you get to future classes, like if you're going to take organic chemistry, you'll likely see molecular orbital theory pop up a little bit again there, and you'll have kind of a little bit of idea of what exactly it is or what information it's trying to give you. Likewise, in 1212, if you end up talking about band theory in your 1212 courses, MO theory has a little bit of application there as well. All right, so the reasoning behind having this kind of separate bonding model from everything else that we've talked about, because like Lewis structures and valence bond theory and Vesper and all that stuff, it's really nice for finding a lot of different pieces of information. Right, we've talked about like how to get geometries and shapes and things like that, but the problem is that most of those different models don't have good ways to give us a lot of times like physical information, like physical properties, particularly electronic and magnetic ones. So things like unpaired electrons that can cause magnetism is one of the biggest things that we just don't get any information about from Lewis structures or from valence bond theory. For instance, I think the classic example that I usually come to here is the fact that O2, oxygen gas, we know experimentally that molecule is paramagnetic, meaning it has unpaired electrons in it. But nothing from its Lewis structure or anything else that we've talked about previously gives us any clue to why that is. And that's why we really have molecular orbital theory. It's another way to think about things to kind of help us differentiate. Right, and so like you will see these terms, and I think I highlight both of these again with their definitions as well. Diamagnetic and paramagnetic. Diamagnetic means that all of your electrons in the whole molecule are paired. If something is paramagnetic, that means there's some number of unpaired electrons. It could be one. In some transition metal compounds, it could be 5 or more. But it's usually just a matter of like any number of unpaired electrons, that compound will be paramagnetic. And we'll talk a little bit more about what that means as well in a little bit. And so molecular orbital theory, it's going to be better at giving us this information for helping us figure out when are things diamagnetic or paramagnetic to help better relate that then to some of these physical properties that we don't get any information about from our previous bonding models or theories. So that's kind of our background for why we need this or why we're going to talk about it. Now, in terms of what are kind of the general basic things about molecular orbital theory? So previously, valence bond theory, everything was about orbital overlaps. Molecular orbital theory is a little bit different. It's actually more, I view it more as like a mathematical way of looking at things. We've talked about atomic orbitals in the past, right? We talked about them back kind of in previous thing was chapter 6. how atomic orbitals are really just mathematical functions, right? They're the wave functions describing where we think an electron is likely to be found in an atom. Well, a molecular orbital is basically the same thing, except instead of being a wave function for where an electron is in the atom, it's going to be a wave function for where the electron is in a molecule. And so it's a little bit bigger picture, but it's kind of a similar thought process, which means these are kind of mathematically based and generated. And so there's a couple fundamental pieces here for molecular orbital theory. One of the biggest ones that I often refer to as kind of the fundamental rule of MO theory is the fact that however many atomic orbitals you start with on the atoms that you're forming any bonds between, that's the number of molecular orbitals that you're going to end up with at the end. And I think that'll make much more sense when we see our molecular orbital diagrams here in just a little bit. But that's something to kind of always keep in mind. It'll always be true for anything you see in MO theory at any level, whether it's Gen Chem level or up to some of our senior classes where we go more in depth with it. That if nothing else, like remember that piece, and then if you know that, that'll help to draw any of the MO diagrams to an extent. But really, probably more often than not, we'll probably have MO diagrams at the general chemistry level, and it'll be more about kind of filling out those MO diagrams and also then figuring out the pieces of information we want, which are going to be really like bond order and magnetism pieces of information. And we'll kind of review those as we go. First, though, how we form molecular orbitals, since they are mathematical wave functions, and I said that they can be very math-based, really what we're doing is just combining atomic orbitals. Right? And so if we want to take two mathematical wave functions and combine them, it can happen in one of two ways. You can have either what we call constructive interference or destructive interference. Constructive interference is what leads to what we call a bonding molecular orbital. So this first one, this is really basically if you imagine having two wave functions that are kind of basically in sequence with one another, like they both have their kind of like peaks and valleys at the same points. So you're effectively kind of adding the two wave functions together. That would be what this bonding molecular orbital is. Destructive interference leads to what's called an anti-bonding molecular orbital. This happens if you have wave functions that are like the opposite sign, basically at the same time. And so that what ends up happening is if you try to combine two orbitals that are opposite in sign at the same time, adding them together, they effectively cancel each other out. And so you don't have any kind of real space where your electron could be in some instances. And all of your anti-bonding orbitals will always have something called a node. Which is something we talked about previously for orbitals as well. And so to show kind of visually what that looks like, if we imagine having two orbitals that we're effectively adding together for the constructive interference part, they're going to overlap. And so here we actually see, probably realistically, this is maybe a little bit more ovalish than what it's shown here in the image. But we get a strong overlap, everything's connected. That would be what we call a bonding molecular orbital. It's a very strong, attractive interaction. For our anti-bonding orbital, that's when these two things would have opposite signs. So either you imagine like having the same sign and being subtracted, or if they were two things being added, but like if this was the blue color initially when you go to combine them. And I think a lot of these images we use blue and pink as kind of like positive and negative to just differentiate the signs of the wave functions. But what ends up happening is with this destructive interference, like at some point in the middle, these two wave functions effectively cancel each other out and they create this what we call node. And what that node is, remember, there's zero chance of an electron then being between these two atoms, which means any electrons that end up in these anti-bonding molecular orbitals, what the net effect of that is they actually weaken the overall bond because the anti-bonding orbitals are all over here and like over here. They're not between the atoms to really help strengthen the bond itself. So bonding molecular orbitals, electrons in those orbitals strengthen bonds. Anti-bonding molecular orbitals, electrons in those orbitals weaken bonds. And again, once we get to looking at what we call MO diagrams, we'll get maybe a little bit better perspective on exactly what that means and the ways that we can figure that out. So, into the diagrams then. What these molecular orbital diagrams are, they're just kind of a visual representation of the energies of your starting atomic orbitals and your ending molecular orbitals. And it may sound really confusing at first, but when we actually start seeing them, it's really not that bad. The things to keep in mind whenever you see a diagram, or if for some reason you ever have to draw one, which probably won't have to draw any for general chemistry, I would guess. But if you get to later on classes like Organic Beyond, you might have to do that a little bit. So something to keep in mind if you ever do have to draw them. Atomic orbitals go on the outside. So you basically have your starting atoms on the outsides, like on the left and the right. And then you're going to have a middle portion that's your actual molecule. And that's where all of your molecular orbitals will be. And I'll show kind of an image of this in just a second. And then for the bonding and anti-bonding orbitals that we talked about a second ago, bonding molecular orbitals always go down in energy from where the atomic orbitals start, and anti-bonding molecular orbitals always go up in energy from where the atomic orbitals start. And so the net effect of all of this, and kind of to show a sample diagram, most of these are going to look something similar to this, although they can get much more complicated, and we'll see what happens when we include p orbitals in a moment. But really, this could be an example for H2 for an MO diagram. We'd have hydrogen, one atom of hydrogen on the left, another atom of hydrogen on the right. They each have one, basically just the 1s orbital. It's the only orbital they have that has electrons, and that's the one electron that we see here. And then what happens, these are the atomic orbitals on the outside. These are those molecular orbitals that I was talking about on the inside. So if two orbitals are going to overlap to form a bond from what we think of normally with like valence bond theory, instead of talking about hybridization, this is kind of an alternative way to try and think about what happens. Instead of getting hybridization, we get these bonding and anti-bonding orbitals, where we get a bonding orbital that goes down in energy from where we started out, and the anti-bonding that goes up in energy from where we started, for just the plain atom, the plain atomic orbitals that you'd have had starting out. And now, in terms of why do bonds then form, for this model, this gives us kind of some nice perspective for why certain molecules exist where other similar ones might not, right? We talked about standard states of elements before. And so for instance, we talked about how if we look at a periodic table, there's, and I'm going to actually back up to so we can see a periodic table here. I think I have it's in here, yeah. So if we look at a periodic table, we talked about how hydrogen is diatomic, and like nitrogen, oxygen, fluorine, chlorine, bromine, iodine, like all of these, this kind of upside down L in the upper left corner, those are all diatomic elements, meaning when you find them in nature, you find them as like O2 or Cl2. But for like our noble gases like neon or argon or helium, they are not diatomic, they're what we call monatomic, which means if you find helium gas in nature, it's just individual atoms of helium, and that's it. MO theory actually gives us a way to kind of help explain why that happens. And so that's one of the things we'll kind of try to work our way towards here as we kind of go through the rest of these slides. All right, so to kind of look at what are the information that we actually want from these diagrams. So from these molecular orbital diagrams, because more often than not for general chemistry, we're probably going to be given the diagrams themselves. And so we have a couple main focuses as far as pieces of information that we're always looking for. We're looking for bond order, and we're looking for information about magnetism. Those are probably the two big things that always kind of come up. That said, the other thing I might kind of add to this at times is you may be given a blank MO diagram and actually have to fill it in. And I'll show you guys how to do that as we get to some examples at the end as well. Now, in terms of these two pieces that we're looking for, though, kind of like the end goal, like pieces of information we can find from these molecular orbital diagrams, bond order. Bond order is something that actually correlates really well to what we see out of Lewis structures. So for instance, if you draw a Lewis structure, if I back out for just a second again, let's say we draw a Lewis structure for N2, right? That's something we've done in the past. So if I zoom out quick and we'll take a look at drawing Lewis structure for N2 real quick. So for N2, when we drew this in the past, we found that this actually ends up having a triple bond and lone pairs in each of the nitrogens. And now if we take this molecule and we want to know like information, like we have a triple bond here from just our Lewis structure. When we go and draw a molecular orbital diagram for N2 and actually look at N2's molecular orbital diagram, when we go to calculate its bond order from the molecular orbital diagram, we should hopefully get 3. Like bond order and the number of bonds from Lewis dot structures should match when we go back and forth kind of between those different models. And so that, which is a good thing, because if they never match, then we'd have problems, right? We'd have an issue like, well, how do we really describe this bond? Like one of these models must not be very accurate, and it's not really the case. They're both usually accurate, but they give us kind of different perspectives or other additional pieces of information, right? Like Lewis structures and valence bond theory, stuff like that helps us figure out shapes. Like the orbital theory gives us kind of, like I said, kind of the electronic structure, and really more than anything, the magnetic picture of molecules that we might not get otherwise. Right, and so the bond order was the one, and then we said the magnetism, and there's the definitions just to reiterate again, right? Paramagnetic, diamagnetic. Paramagnetic just means there's some number of unpaired electrons in the whole molecule. We'll see an example of oxygen gas in a moment, and that it's actually paramagnetic, even though Lewis structures can't really tell us that. And then we'll see some examples that are diamagnetic as well. Turns out nitrogen gas is diamagnetic when we get to that one. Now, how we go about finding these things, bond order, it's actually not too bad, and it's really just a kind of a simple equation. And so how we find the bond order is we're going to take the total number of electrons in all of the bonding molecular orbitals, so basically the middle orbitals in those diagrams, minus all of the electrons in anti-bonding orbitals in those diagrams, and then divide all of that by 2. So for instance, if I show that example with hydrogen again, if we're trying to kind of label our different pieces here, like if we're calculating bond order, we only care about the middle orbitals, not the outsides. So only looking at the middle orbitals, we have 2 electrons in, this is the bonding molecular orbital. And again, the way we know it's bonding, it went down in energy from where the orbital started. The other way to know, anti-bonding orbitals will pretty much always have this little star symbol with them, right? And so this is called a sigma bonding. This is a sigma anti-bonding. The sigma is because if you have 2 s orbitals, the only type of bond you could make is sigma, based on the way we talked about sigma and pi orbitals previously. And so that's why they're labeled with the sigmas there, because the s orbitals can only make those sigma bonds. But we have the sigma bonding, and then the sigma star represents an anti-bonding orbital. So in this case, if we're using this diagram to calculate bond order, we'd have 2 electrons in the bonding orbital, right, because that's what the 2 arrows down here are, minus 0 in the anti-bonding orbital, because it's empty, and then dividing that by 2 gives us a bond order of 1, which should make sense, because if we think about drawing a Lewis structure for just hydrogen gas, the Lewis structure for just hydrogen gas, if I zoom back out for a second, right, Lewis structure for hydrogen gas is just that, right? It's just a single bond between the 2 hydrogens. So again, we should see that matching hopefully with bond order and Lewis structures for most of the examples that we take a look at. All right. So if we want to look at some things that we can then do with molecular orbital theory that maybe Lewis structures don't give us as good of a picture for. So here we have an example of taking a look at some other examples. So I have up here like He2 plus and He2. So here would be the He2 molecule. This is labeled as H2 minus, but since all we're really looking at is electrons, He2 plus and H2 minus are effectively the same thing for this diagram, at least from our perspective at the moment. In reality, the actual like spacing of some of these orbitals would be slightly different, but for our intents and purposes of just looking at putting the electrons in, both He2 plus and H2 minus have 3 total electrons. And that's the part about filling these diagrams that I wanted to get to. So if we have just an s orbital on our outer atoms, which for hydrogen or helium, that's the only orbital they have is just a 1s orbital. It's the only orbitals that have electrons anyway. Then if this was He2 plus, one of the heliums would have a positive charge, there'd only be 1 electron in it. This one over here has 2 electrons. What you should always see in your diagram, the number of electrons on the outsides total will always equal the total number of electrons in the middle. You'll always see those 2 things kind of match together. So if you have 3 electrons on your outside kind of starting orbitals, you're going to put 3 electrons into your middle orbitals, and you always start at the bottom and basically just work your way up. And you will follow Hund's rule, and I'll show an example of that as we talk about p orbitals as well, and what some of their images for these molecular orbital diagrams will look like. But this information then that we're able to get out was as we kind of draw these diagrams for these different molecules. So for H2 minus or for He2 plus, this MO diagram, if we calculate the bond order, we'd have 2 electrons in the bonding minus 1 in the anti-bonding over 2 would be 1/2. And really, anything that has a bond order that's bigger than 0 can potentially exist. That doesn't mean it's going to be very stable. It might not exist for very long, but there's this potential that it has some energetic potential to maybe be able to form. And what I mean by that is if you look here where all these electrons started out, this is really an energy picture, right? All of these molecular orbital diagrams are really just energy maps, where the lower down you are, the lower in energy, really the more stable things are. And so you'll notice if these are where 3 electrons started out, 2 of our electrons went lower in energy, 1 went higher, the average energy of our electrons at the end in the middle is lower than what it was at the start, right? Even though 1 got higher energy, 2 of them got lower by about pretty much the same amount. And so because of that, our end kind of combination is more stable than just the individual atoms were by themselves, which means that there's a good chance these things will form a bond. But what happens is if we get just plain helium, like He2, and we try to make like diatomic helium by putting 2 helium atoms together, now if we fill out this diagram, each helium atom has 2 electrons. Well, our bonding and our anti-bonding orbitals are now full, and now we get a bond order of 0. And anything with a bond order of 0, there is no energetic reason for them to want to basically make a molecule. Because what happens is, excuse me, what happens, you have these 4 electrons starting out, that this is their average energy initially. Now you have 2 at a lower energy and 2 at a higher energy, but effectively your overall kind of average energy of your electrons is kind of canceled, right? It's the same as what it started. The only difference is now you have 2 atoms that you've tried to push really close together to make a bond, and probably what's going to happen is those 2 atoms will actually just kind of repel each other a little bit in a way. But just the electron clouds on each of them will probably help to push them apart. So you end up not making any kind of bond because there's no energy reasoning as far as like your electrons being a lower overall energy for that bond to want to form. Whereas over here, and with the hydrogen example in the previous slide, if we had a bond order of 1/2 or 1, overall our electrons are at a lower energy for making the bond, which means there's now some energetic reason to want that compound to form. Again, doesn't mean it's necessarily going to be really stable, but there's a chance that it could be once it's actually made. It just kind of depends. All right, so everything we've looked at so far is looking at kind of our simplest model of molecular orbital diagrams. So there's hydrogen, helium, so really small atoms. We're going to branch out to the second row, and we're actually not going to go beyond that because I can't imagine for general chemistry that we ever need to know more than anything about MO diagrams for like beyond the second row of elements. So we'll really just take a look at our second row elements. Things like for lithium and beryllium. It turns out it's going to look pretty much exactly like we just saw. So lithium and beryllium are going to look just like this, except instead of 1s here, there'll be 2s. Because the reality is like they're each going to have the 1s, but each of them will have a full 1s, so it'll just look like this, which the bond order is 0 when those orbitals try to interact. So this really does nothing. So most of the time for these MO diagrams, you probably will only see the valence shell of orbitals, kind of your outermost energy level. So like your second row elements, a lot of times you'll probably only see the second row orbitals included in those MO diagrams. Not always, but most of the time, it'll just be the second row orbitals. And so for lithium beryllium, it'll look almost identical to what we just saw, just be 2s instead of 1s. Not a whole lot different for those. Now, for us, though, we do care about the other elements in the second row that are now in the p block. And that's where things get a little bit more interesting. We're not going to worry about d orbitals at all. Things get a lot different when we start to look at those or include those. If you're interested in this kind of thing, we talk about this kind of stuff in like inorganic chemistry and some of our upper level courses. It's kind of a shameless self-plug for myself since it's one of the classes I teach as well. But if it is something that's all interesting, there are upper level classes in chemistry where we do get to talk about this stuff more. But for general chemistry, probably not going to be very relevant for us. So we're going to stick to just the second row elements. And stick to really the diatomic ones, and we're not going to get any bigger than 2 elements for any of our molecules that we look at. The one thing we do want to keep in mind, though, is if we go to now kind of the P block of that second row, right, just to show the periodic table here for us, so that we have it. Right, if we're looking at our periodic table, second row, so here's our P block in the second row. So for any of these elements, for their diatomics like B2, C2, N2, O2, F2, or Ne2, for all of those, we want to have an idea of what are their molecular orbital diagrams actually look like, because they are going to be a little bit different. And so there's going to be a couple changes that occur. And the biggest thing is that previously, like when we had just hydrogen and helium, each atom only had 1 atomic orbital, right? They just had the 1s. But if we start including p orbitals, there's many more, right? Each atom has 3 p orbitals in that second energy level, which means there's actually going to be 6 total molecular orbitals that we make in the middle. So there's a lot more going on in the MO diagram of that P block than there was previously in kind of the S block examples that we've looked at so far. So to visually look at this is probably going to look really intimidating at first, but I'm going to try my best to kind of explain what's going on here and give you some kind of reasoning for some of the things that you're seeing. And so first off, you see kind of 2 different variations of really kind of the same plot in a lot of ways. What I'm going to focus on is mainly this upper part right here. These are the p orbitals and kind of what's going on with the p orbitals. Down here's the s orbitals. This is pretty much what we've already looked at. Nothing's, right, if we look at this looks exactly like we saw before, but just 2s instead of 1s. So nothing new there. But this is different, right? And in fact, we actually see that nitrogen and then oxygen and fluorine actually have slightly different looking kind of organizations. Probably not going to need to know why that is for general chemistry. If you're really interested, it's really just about electronegativity. The more electronegative the elements, they're going to follow this type of pattern. The less electronegative the elements, we get some weird what's called mixing in our orbitals that actually causes what should be what we would think would normally be our bottom one down here to actually move above these pi ones. And so I'm going to go into kind of detail about where all of this actually kind of comes from. And I think it's probably easiest if I actually show an image of this and draw it. The next couple slides do show some kind of visual images on the slides. Personally, I usually like drawing these to kind of give people a better feel for what's going on. So what I imagine as far as where those kind of diagrams come from, if you have two atoms that have their sets of p orbitals, right? If we think about our p orbitals, if we have a p orbital that's up and down, one that's going left to right, and I'll try to draw this as best I can, kind of in and out, right? That would be the orientation of p orbitals around any one atom. Well, if I had a neighboring atom that had its p orbitals arranged in the same fashion, to bear with my very, very challenged artistic skills, especially on an iPad, I apologize, right? If we think about trying to push these two atoms close together so that they make a bond, these two p orbitals can interact end-on, right? That's a sigma-type bond between those two p orbitals. We often label those as the pz orbitals, although that might look weird to have the z going left to right on this image, but that is often how they get labeled in this case. And then we also have these p orbitals that would have to interact side-on, right? That'd be one pi bond. And these p orbitals, if we push things close enough together, can make another pi bond also in that kind of side-on fashion. And so if we think about this, if we have this sigma bond right here, if we make a sigma bond between two atomic orbitals, that means we get a sigma bonding orbital and a sigma anti-bonding orbital. If I go back to these diagrams, in both cases we have, regardless of which kind of order of things, we have a sigma bonding and a sigma anti-bonding, right? So like a plain sigma and a sigma star for each of them. If we look at, then we have two different pi bonds that have occurred. Well, if we have two pi bonds, that means we should have two pi bonding orbitals and two pi anti-bonding orbitals. Well, here's two pi bonding orbitals and two pi anti-bonding orbitals. So that's kind of where all that's coming from. We're basically just leaving the p orbitals on the atoms themselves and look at, as we try to push these things together and make them overlap, what kinds of bonds can we form? And we can get one sigma and two pi bonds out of those p orbitals potentially. And so that's where those labels come from. And again, for the order on things here, whether like the pi is on bottom or the sigma is on bottom, I really don't think that's something that's important for general chemistry. Like I said, it is due to electronegativity. Electronegativity, the more electronegative, the more likely you are to have the sigma on bottom. So like oxygen and fluorine, neon, if it ever came up, would have the same. Nitrogen and anything to the left of it, like boron or carbon, would then look like this with the pi on bottom instead. But I think that's probably more than anyone really needs to know for most examples, and that's what I kind of make note of down here. Now, what do we actually want to do with these? Well, the biggest thing we want to do is just be able to really fill out these diagrams and figure out what information these things can tell us. And so to look at actually going through that process, what I'm going to do is I'm actually going to draw the molecular orbital diagram. And so I can actually here, I think I have a couple more visual images showing some different things, but really I'm going to skip to the examples. These three slides basically show and demonstrate the same things I'm going to show out of these examples. And hopefully these examples will kind of demonstrate everything that you really want to be able to do or know about these MO diagrams in terms of being able to use them or answer questions for anything for this class. So we're going to take a look at, for our whiteboard example here, the first one just wants us to draw, basically, it doesn't have the MO diagram listed, so it wants us to figure out the bond order of N2 and figure out is it paramagnetic or diamagnetic. So what we want to do is draw an MO diagram for it. So what we're going to do, here we go. For these molecular orbital diagrams, we have our plain starting atoms in the outsides and the full molecule in the middle. Right? For nitrogen, we have 3 p orbitals on each of our starting atoms. We also have the 1s orbital on each of them that's lower in energy. And so these two s orbitals, what's going to happen? We can get an anti-bonding orbital that goes higher, a bonding orbital that goes lower. And in terms of filling things out in a second, and I'll do it kind of all the filling out in a moment, for filling out all of your electrons, it's really just taking your electron configurations, like your valence electrons, and looking at what you have. So we said these are our 2s, right? So this would be a sigma and a sigma star, right? So we have bonding and a sigma anti-bonding, and we know it's sigma for each of these because it's an s orbital. For the p orbitals up here, these would be our 2p orbitals on each of our nitrogen atoms. From the image that we saw, we actually already know that the bottom set is actually 2 orbitals. That's a pi bonding set of molecular orbitals. And then we actually have a sigma bonding molecular orbital. That's also, and we know all 3 of these are bonding molecular orbitals because they're lower in energy. And then we have at higher energies, we have the pi anti-bonding, and the order at the top is actually always the same. So pi star, and then the very highest one is always going to be the sigma star for these drawings. And what we want to be able to do is most of the time, like you're going to be given this diagram probably to start. What we want to do is just have you be able to fill it out, right? So if we go to fill this out, what we're going to end up doing is basically look for nitrogen on the periodic table, like how many valence electrons does it have? Well, if we go to a periodic table, right, nitrogen's right here, so 2s2, 2p3, it's got 5 valence electrons on each nitrogen. So what that means then is on each outer atom to start with, the 2s is full with 2 electrons, and there's 3 electrons in the 2p. What that does for the whole molecule then for all of our inner orbitals here, right, these are the molecular orbitals for the whole molecule. If there's 5 electrons here, 5 here, that's 10 total. There should be 10 total electrons in this middle part that we're trying to fill out. And so putting in those 10 electrons, we're going to follow what we call Hund's rule, which basically means we start at the lowest energy orbital and just work our way up. That'll never change. You always start at the bottom, and basically until this orbital's full. Once this one's full, then you go up to the next one and repeat. So we'll fill this bottom sigma bonding. We'd have 1, 2, 3, 4. And remember, we have 10 electrons to put in. And the other part of Hund's rule, if we have 2 orbitals that are the same energy, which is what these 2 pi orbitals are, then what's going to happen is we're going to put them in one at a time and then pair them, right? So we've added 4, so this would be 5, 6, 7, 8, adding things in, and then 9 and 10 in that sigma bonding orbital. So those would be all of our electrons now added to this MO diagram. Now, the pieces of information we want to find, right? The magnetism one, I think, is always the easy one, right? We want to know, is it paramagnetic or diamagnetic? And so I'm just over here going to write para or dia for the type of magnetism. And for this part, you only care about the middle. The outsides do not matter. We're just looking at the middle. And if everything is paired on the inside, remember that is diamagnetic, right? So this thing is diamagnetic because all of our electrons are paired. And then the other piece of this, our bond order, right? That's going to be our number of electrons in bonding molecular orbitals. So basically all the orbitals that don't have the stars on them, minus the ones in anti-bonding, which is the ones that do have the stars on them. So here's a bonding orbital, right? It went down in energy from where these orbitals started. So there's 2 electrons in this bonding orbital. This one's anti-bonding, so we're not going to count that yet. All 3 of these are bonding orbitals because they're all lower in energy than where they started, and there's no star symbols with them. So that means we have 2, 4, 6, 8 total electrons in bonding molecular orbitals, minus, if we look at our antibonding, here's an antibonding, there's our other antibonding, there's only 2 electrons in the antibonding orbitals. And we're going to divide all of that by 2. So 8 minus 2 is 6, divided by 2 is going to give us 3 for a bond order. And remember what we said earlier for nitrogen. And I'm just going to scroll up just real fast because I had drawn it up there. Nitrogen was a triple bond. Well, lo and behold, when we draw the MO diagram, if we've done everything correctly, we get a bond order that matches that triple bond order of 3. So there are a lot of nice things that kind of correlate between things that we've done previously and this molecular orbital theory. They should hopefully work nicely in tandem. And they'll also give some other clues, like for instance, N2 is diamagnetic, O2 is diamagnetic, things like that, but C2 is not, right? If we think about trying to draw a Lewis structure for something like C2 and how we would actually try and do that, if each carbon only has 4 electrons, there's only 8 electrons total. Well, that would mean that if I tried to do my normal rules, I'd fill a lone pair here and had nothing left for that carbon. Well, this carbon the right carbon now only has 2 electrons, so I'd have to make a double bond, getting rid of 1 lone pair. Then I could make a triple bond, getting rid of another lone pair. But I still don't even have an octet on that other carbon, which means I'd have to kind of technically make a quadruple bond, but you can't actually do that for elements that don't have d orbitals. And so carbon can't make a quadruple bond to itself. So C2, like Lewis structure-wise, there's no good way to explain what's going on. But it turns out, if we think from like a formal charge perspective, probably the best thing that C2 could probably look like would be something like this. Neither carbon has an octet, but they each at least have 0 formal charge. And if we draw the MO diagram of C2, it would actually come out to be 2 for a bond order to kind of go with this. The problem is you don't actually see that for carbon because, well, how stable is something that doesn't have its octet right there? The answer is not very stable. So C2, you don't see to C2, it makes other compounds instead. And if you know a little bit more about carbon, it likes to make like graphite or diamond, for instance, as different forms of its kind of elemental form in nature. And so that there's different ways it can organize that are not just diatomic molecules like what we get for N2 or O2 that are very stable. All right, so there's kind of, and like I said, this is pretty much the full process. I drew the diagram itself. Probably the most, I think, like I said, you can probably expect it to do is fill in this diagram with the electrons. So like fill in the outer atoms first, find your total, start at the bottom, and just add them until you don't have any electrons left. And then the paramagnetic diamagnetic, we're just seeing are there unpaired electrons in the middle or not? And the bond order, just bonding electrons minus antibonding all over 2 to find the bond order. So one more piece then, and then we'll use this last example to kind of wrap up. And this is probably the biggest extension of anything I could see ever getting asked of this topic anyway, for general chemistry. And that's something along the lines of which of the following would have the shortest bond length between O2, O2 minus, and O2 plus. And if you're able to answer this based on MO diagrams, I think that's a clear indication that you have a pretty good feel for what information those diagrams are trying to tell you. And so to figure this out, it's not as simple as just looking at, oh, well, O2 is neutral, it should be the most stable, or O2 minus has an extra electron, so it should be more stable. And that's not really what's going on. To figure this answer out, if you're asked to compare things like this that are, different ions of molecules that are similar to each other, which one has the shortest bond length, you have to look at an MO diagram. Like that's how you're going to differentiate that information. And so to do that, we're going to need to actually look at an MO diagram. So I'm going to go ahead and scroll down, give myself some space. We're going to make an MO diagram for O2. Try to draw this one a little quicker, just since you already saw me draw the example for nitrogen. So this is our example for O2. There are two s orbitals. We have a sigma and a sigma star. Then we have our two p orbitals. And remember, for oxygen, the bottom one is actually the sigma, and then the pi. And then the top is always the same for all of these, which is pi star, and then the sigma star on top. All right, so for oxygen, what we want to do is basically let's start with O2. And if we're trying to figure out like which of these has the shortest bond length, we want to think back to what we've said previously about bond lengths and bond strengths. The shorter a bond gets, that's because it's a stronger bond. So if we want the shortest bond length of all of these, really what we want to figure out is which of these three variations has the largest bond order. That's what we actually want to find. And the one with the biggest bond order, that's the one that should have the shortest bond length between the atoms. So to figure that out then, oxygen has 6 valence electrons, right? So it'd be 2s2, 2p4 for each of these on the outsides. So I'm going to add our electrons here. So it's a total of 6 electrons from each oxygen. So we have a total of 12 electrons on the outsides, which means now we are going to put 12 electrons in the middle. We're going to start at the bottom. So I have 1, 2 in the bottom sigma bonding orbital, 3, 4 in that sigma star, 5, 6 in the sigma bonding from the p orbitals, 7, 8, and then 9, 10 for those pi bonding orbitals in the p orbitals. And now we have the pi anti-bonding that we still have 2 electrons left that are actually going to go in unpaired. Right? And remember one of the things I said at the very beginning about O2 that's kind of unique? O2 is paramagnetic. It does have unpaired electrons. Experimentally, we can show that. And then really how we can figure that out is how things interact with a magnetic field. Paramagnetic compounds are usually attracted to a magnetic field. We can get them to interact with it very strongly, whereas diamagnetic compounds are often repelled by magnetic fields in terms of kind of how they will often cause like things to behave. Now, when we look at this in terms of answering our question that we started out looking at with O2, O2 minus, O2 plus, what we want to figure out is what is the bond order for O2 initially? Well, if we want to find this thing's bond order, we're taking all of our electrons in the bonding orbitals. So 1, 2, 3, 4, 5, 6, 7, 8, right? Because here's our three bonding orbitals for the p and then the one for the s down here. So 8 total electrons in those bonding orbitals. minus, here's 2 in antibonding for this sigma star and 2 more in this pi star. So minus 4, all divided by 2, that's a bond order of 2. So if we think about this just real quick, Lewis structure for O2 is this, right? It has a double bond, so that's good. That makes sense. Now, to answer our question, O2, just neutral O2 has a bond order of 2. What happens if we make this, instead of O2, we make it O2 minus? We add an electron. So O2 minus adds an electron. That means I'm going to add one, the next electron would go right here. As soon as I do that, what have I made? Well, now what I have is, in terms of my bond order, instead of 8 minus 4, the electron I added was to an anti-bonding orbital. So this was O2. For O2 minus, my bond order is now going to be 8 minus 5, because I have that extra electron in an anti-bonding orbital. Ooh, sorry about that. So now my bond order is only 1.5, or 3 halves. So my bond actually got weaker when I added that electron, which means now if I do the opposite, if I take an electron away from just plain O2, let's see if I can selectively erase this properly. Here we go, it's not bad. So there's taking away the electron to get back to O2 neutral, but now to take away an additional electron to get to O2 plus, right? So I'm going to draw this as O2 plus now. So for O2 plus, now if we calculate the bond order, I have 8 minus, I took an electron out of one of the anti-bonding orbitals, it's 8 minus 3, which now means I have a bond order of 2.5. Oh, I'm sorry, I keep hitting my scroll mark there. Bond order of 2.5. All right, so bond order of 2.5, we're comparing these to a bond order of 2, 1.5, 2.5. If we want the shortest bond, we want the highest bond order. Here's our highest bond order, which actually means then O2 plus, this last example here that we've drawn, should have the strongest bond, which is then the shortest bond as a result of that. So O2 plus should have the shortest bond of this bunch. And so this is another application kind of molecular orbital theory. And like I said, this is probably the hardest application of any of this kind that I think we would ever see, is being able to answer questions like this one, like in terms of like talking about bond length of different ions of the same kind of like diatomic molecule, and having to look at them basically with MO diagrams to figure out the bond orders. And you do want to be very careful, because it's not always just that the cation has the highest bond order. That's not always going to work. If we had been asked about like N2, N2 minus, and N2 plus, it turns out neutral N2 is actually the highest bond order. And so you really just have to draw the diagrams to figure that out, is kind of what I would suggest for any question like that would ever come up. All right. I think that's probably more than enough MO theory that we've probably gone through. I know this is a topic that different professors will cover probably much less of than what I just did, and that's okay. But hopefully now, if you ever see this again in like organic or other classes, you have at least enough of an introduction to this to know what's kind of going on or being talked about. And like I said, at the very least, if you can at least answer questions about bond order and like diamagnetic, paramagnetic, that's probably the big focus, I would say, out of most of this material, because that's kind of the most common questions that are usually asked regarding this topic. All right. The next time we have our next recorded lecture, it'll be for Chapter 10, and so I'll be starting into gas laws, and hopefully I'll have that up in the next couple of days. I'll see you all next time.